We're going to start a new section today. It's called cylindrical coordinate system. We're going to use it to help us to integrate as well. So what does a cylindrical coordinate system look like? And this is my very bad attempt to draw 3D. But can you imagine you have a point in space called P, and its X, Y, and Z is its normal coordinates. But you could tell people where its location is in terms of the polar position on the XY plane, and then go vertically upwards in the Z. And when you do that, it's called cylindrical coordinates. Now, when we did R and theta, wasn't it called polar coordinates? So can you think of cylindrical coordinates as polar coordinates in the XY plane and just let Z stay as Z? Quite an interesting thing. Why is that useful? Well, it allows us to find triple integrals much easier than if we left them as X, Y's, and Z's. In fact, yesterday, I believe we did at least one question where we turned it into polar, didn't we? Wasn't there an XY that we turned into polar? Because it was easy to, yeah. Well, that was actually cylindrical coordinates. We just never called it that. So you've kind of sort of seen it. So let's do a couple of intro things. Suppose I gave you the point 2, -2, 4. And I'm talking about in X, Y, Z, right? Cartesian coordinate system. And I wanted you to turn that fella into cylindrical. Well, let's do the easy one first. The Z is still 4. And X and Y is 2, -2. So if you imagine 2, -2, it would be essentially here. And so the R and the theta go next. Well, if I wanted to tell you where this point was, wouldn't I need to know the length? Because that's essentially R to this point. And that's what? The square root of 4 plus 4, which is what? The square root of 8, which is 2√2. So that goes there. And the angle, I could either measure it this way, or I could measure it that way, and both are correct. If I decided to go in this direction, wouldn't the angle be a negative number? I've chosen really nice numbers. Do you recognize this is going to be 45 degrees or pi upon 4? So I could call it negative pi upon 4, or equivalent to that, I could call it, if you go the positive direction, that guy. So converting from Cartesian to cylindrical is just a matter of leaving the Z coordinate alone and using the 2 X and Y coordinates to figure out what the angle and the value of R is. And the value of R goes here and the angle in radians goes there, and you are finished. Another skill building. How to convert functions from Cartesian X, Y, Z into cylindrical. So suppose Z was X squared plus Y squared. Then if you wanted to turn that into polar, couldn't you basically just say, oops, that it was R squared. Suppose Z was 2xy. Then that would be 2 lots of R cos theta followed by R sin theta, basically using these two. If I tidy that up a little bit, I get that. Yet, you might not actually see that. How did this become that?
Half angle identities?
Well, double angle identities. But if what you meant was that the sine of 2 theta is 2 sine theta cosine theta, then yes, that's where it came from. Let's try something a little bit crazier. Just losing some over here. How about 4x squared plus 2x plus 4y squared plus z squared equals 9. And I want to convert that into polar. And in particular, I always want to try and convert it into z equals. This fella, 4x squared, and this fella, 4y squared, if you put them together, would you agree you get 4 lots of that? You then have a 2x, you then have a z squared, and it equals 9. And doesn't that guy become 4r squared? And what does this guy become? 2r cos theta, and that guy stayed the same. And then you subtract that from both sides. You subtract that from both sides. And then you take a square root. And we'll assume in this question that z was positive, which means it's above the xy plane. So this shape, and it's a surface really, in 3D space becomes this fella in polar. In polar, in cylindrical. Although technically it's polar as well at the same time, isn't it? What would z equals 3x squared take away 3y squared look like? Well, 3 lots of x squared take away 3 lots of y squared. That becomes 3r squared cos squared theta. Take away 3r squared sine squared theta. Pull out the common factor. That guy is 99% right, but he's not 100% right. That guy can turn into something nicer.
1.
If that was a plus, I'd agree with you. Anyone get the cobwebs? Yeah, you got it. I was going to say get the cobwebs out your brain. It's that guy. Now, why is that better than this? Can you imagine you're going to have to integrate these things? Isn't that a lot easier to integrate than this? And isn't this a little bit easier to integrate than that? Nobody in the world wants to integrate this, right? So let's see what we've done. If I gave you a point, a Cartesian point, right? 3, 6, 1 or whatever, do you feel you could convert that into cylindrical if you needed to? Probably aren't going to ask that much more than about once. If I give you a function of x, y, and z, do you feel that you could rearrange that into its Cartesian stroke polar version? Not Cartesian, it's cylindrical polar version. So z equals r squared plus 2r cosine theta, that kind of look. Okay. Well, let's put the package together. This is a version of question 3. We have a triple integral. It's going to be the square root of x squared plus y squared dv, which is pretty standard. And the region E is described as it lies inside one cylinder and between z equals -4 and 1. So it's inside x squared plus y squared equals, say, 1. And it's between -1 and z equals 4. So that's E. So let's see if we can set this fella up. The dv that we're going to do is going to be r dr d theta dz instead of dx dy dz. Are you all comfortable about where that funny r is coming from? Now we're going to take every piece of this puzzle and convert it into numbers or r's and thetas. Right, so let's see what we have. What's this equal to?
R.
That was easy. R dr d theta, right? In this case here, doesn't z go from -1 to 4? And isn't this an entire circle, radius 1? So that means I could do theta equals 0 to theta equals 2 pi, and r equals 0 to r equals 1 of r dr d theta dz. Now, in this particular question, the triple integral that we've been asked to evaluate, do you see it's now changed into this fella? If you do it correctly, for cylindrical coordinates, if you do it correctly, this expression here will only have r and theta in it, right? You won't have any z's. Right? These guys here will be r, theta, and z, but they can permutate. Sometimes you do z first, you know, and r second, and theta last, whatever the combination is. In this particular case, this works. Would you agree that this is a variable separable question? So in that case, let's do it. That's going to be one of these guys, dz. We're going to go from theta equals 0 to 2 pi of 1. And then this last guy, well, r equals 0 to 1 of r squared dr. That guy there is 5. That guy there is 2 pi. And this guy there here is 1/3 r cubed, which ends up being 1/3. You put this package together, and I believe the answer is 10/3 pi. So it's not that, I don't think anyway, it's that big a jump from just normal, typical triple integrals where things just stay as x, y's, and z's, right? We get an added twist that the x and y's get converted into polar restrictions, and that the function, whatever the function is, gets converted into r's and thetas, because this function here is always going to be the z guy, right? This is version of question 5. We have a triple integral. That's this guy. E, well, it's described as inside one cylinder and outside another cylinder. So it's described in generic ways like this. And z is equal to y plus 5. Oh, and it's above the xy plane. So I am going to do a triple integral, and I'm going to do the z first. In fact, it's not actually that uncommon that z always is done first. Now, let's take care of these two guys. In polar form, isn't this basically little circle, big circle, everybody in between? Right? Won't the radius be 3 and 1? So if you think about r equals 1 to r equals 3 and theta equals 0 to theta equals 2 pi. Don't those two basically give me this region which represents that? Now Z is the sneaky one. First, it's above the XY plane. So that means it starts at the XY plane, which is always Z equals 0. So if you start at the floor, Z is 0. Now the finish of Z is this fella. Well, I need this to be written in terms of R and or theta. And isn't Y R sine theta plus 5? So this piece of information gets converted into R and thetas. So it's from Z equals 0 to R sine theta plus 5. Now you notice the order I'm doing this thing in, right? DZ, RDR, theta, that kind of thing, right? Guess I could bring the R in later. X take away Y is going to be R cosine theta take away R sine theta. So this triple integral is now converted to cylindrical coordinates. Yeah, it's going to get a bit messy. I'm going to pull out an R as a common factor, and I'm going to bring this R in, and that leaves me with an R squared, a cosine theta, take away a sine theta, a dz, a dr, and finally a d theta. Are you happy about the tidying up the rearrangements that I had to do here to just get it all together in one place? Always a good question to ask because it happens a lot. Is this a variable separable story?
Eventually.
Right? So can't I pull out the R squared and the cosine sine theta? Right? So what's that going to look like? Well, theta is going to go from 0 to 2 pi.
I think you'd have to do the Z integral first.
Oh, shooting space. Take it away. Well cut. I am not allowed to do what I was about to do because for some strange reason, I forgot to look at this. For a moment, I thought it was a 5 or something, right? Now, if that had been a number, what I was about to do would have been perfectly correct. But you caught me in time, which is a good thing because it means you know what the heck's going on. So let's basically take this guy, right, and integrate it with respect to Z. So, something to my paper. Theta equals 0 to 2 pi, R equals 1 to 3. This expression doesn't even have a Z in it, so technically speaking, isn't that what you get? It's like 5 gets you 5Z. Ugly mess Z. Evaluated at 0 and evaluated at R sine theta plus 5. And then I can do the dr d theta thing. So we now have the integral from theta to 2 pi. This guy goes here, nothing gets you nothing, so what we're going to get now is an R sine theta plus 5 times a R squared cosine theta take away sine theta dr d theta. Oh, God in Himmel. I was just looking at their solution. Mine's isn't quite the same, but that doesn't matter. And they get the exact same problem. Oh, God, that is ugly. And it is not variable separable. I wish it was. If it was variable separable, it would be 10 times easier, but it's not. Which means that the only thing that you can do is the only thing you don't want to do. I'm going to have to FOIL this whole thing out. I'm not doing it. I'm going to go ... and say, that's what you would do. Now, can you imagine when you do it, you're going to have r cubed sine theta and r squared cos squared theta and all sorts of combinations of r sines and cosines. And that is going to challenge you by sheer coincidence. That's exactly what my Calc 2 are doing right now, how to integrate trig functions. So, side issue. Imagine that you had to integrate that guy. Let's just think about how you would integrate just that one particular problem, right? Now, do you know if there's an r squared next to it, can't you just forget it and stick it outside and tag it on when you're finished? So that ain't a major issue. Theta is going to go from what, 0 to 2 pi anyway, right? In our question. How do you integrate that guy?
You turn it into, I think, 1/2 1 minus cosine or 2 theta?
Pretty close, 1 plus. And then distribute it. And then, oops, 1/4. Integrate it. And then boom, boom, boom. How would you integrate a cos cube theta? Because there's a good chance you're going to get one of them. Oh, by the way, you do sine squared almost the same way, but that's a 1 minus. Right. Cos cubed.
Break it up into sine, break it up into cosine squared and then cosine.
Correct. What's the next step?
Turn cosine squared into 1 minus sine squared.
I wish you lot were with my Calc 2 class today. Because you could then say to them, it's important that you remember how to do this because you're going to see it in other places. And guess what? We're seeing it in other places. Right. Perfect. What do I do next?
I believe that's a u sub.
Yep. And what's the u sub going to be?
Sine of theta.
And can you trust me on this that you eventually get that guy? And then 4 lines later, whatever, you've got your answer. And you're good. Right. What other combinations? You could get, let's pick an easy one. You could end up with a term that looks like that. It's not unusual. Could happen. In fact, that ugly one that I did ... to, I'm pretty sure that'll appear somewhere or something like it. How do you tackle that one? That one.
U sub,
Correct. Which u sub?
cosine.
And off you go and it works. Okay. So all those little tricks of the trade that you did in integrating trig functions have now reared their ugly head, haven't they? So I get to say my little sentence. Every single thing that you have learnt in math from 94 onwards does not go away. Some things you might not see for a year. Like how do you integrate cos cubed? But that doesn't mean that you'll never do it, right? You've got to be able to do anything, whatever comes up. This one here is similar to question 6. We have a triple integral over e, and the function's called x squared in this case. And what do we know about it? It lies inside x squared plus y squared equals 9. It lies above z equals 0, and it lies below. Oh, looks weird. It lies below z squared equals 36x squared plus 36y squared. And let's put that word. It lies within that guy, above that guy, and below that guy. And that package has to get put together, right? Okay, we know that they all look like this. Well, let's be consistent. Theta equals R equals. Since you lie within this fella here, is it not basically your x and y guys? And that's going to be 0 to 3 and a 0 to 2 pi. Now, if you're above z equals 0, that means that goes there. But what on earth does this give me? That's the problem.
6R?
Oh, well done. You did it all. Right. Do you want to tell the rest of us where that 6R came from? Because it is exactly correct.
Just do a square root.
And you recognize that guy as 36R squared. And that's where your 6R came from. That went really smooth. I was expecting that to be uglier. Now, technically, there's a plus and minus when you do that, but I'm only going to use the plus. And why do I know that I'm only going to use the plus?
Above 0.
Yeah. Now, see if they didn't have this restriction. Wouldn't I have just changed this to negative 6R to plus 6R, right? If they hadn't the restriction that it was, you know, above z equals 0, right? The top half of the world, whatever you want to call it. Are we good? Right, x squared, well, won't that turn into r squared cos squared? I'm going to have a dz and r theta mess. This guy's going to go 0 and 2 pi. This guy's going to go 0 and 3. That r cubed, and oh, here's a thing I can show you.
I thought that the limits for z were 0 to 6r because we had the above 0
Yeah.
0.
So, well caught. I can't totally separate the variables, but
Shouldn't that be cosine squared theta?
yes, I can't totally separate this variable. My mind's thinking of what I'm about to say here right now. That's why I keep screwing up on the things here. But I can do, there we go. I can do something about this. Isn't this basically a constant as far as dz is concerned? So it might not. It might help you to think of it.
It would still be R cubed.
R cubed. Oh, because of that one. Thank you. I'm not sure if that helps, but it's a different way of looking at it. If you pull this out, can't you just do this guy and then multiply it by that and you're into the next level? Or you can keep it here and give it a Z and plug in that. If you, whatever way you do it, you're going to end up with this line. That guy's basically giving you another 6R. So it's going to be this fella, dr, d theta. And now I get to say what I was hoping I could say. Is this one now variable separable?
Yes.
And that is probably worth it, isn't it? In this case, to separate them out. So you would do the integral from 0 to 2 pi of cos squared. And then you'd basically do the integral from 0 to 3 of that guy. That guy's just a power rule. And haven't we already looked at how you deal with that guy? You convert him into a half, 1 plus the cosine of 2 theta. So it'll take a little bit longer to do this one than it probably will to do that. But when you stick them together, it is done. Are we getting a bit of a feel for cylindrical coordinates in triple integral type situations? Right? You got an r and a theta that are going to be numbers typically, right? Those guys you're going to work with. And then you've got the z guy that has to be converted into something to be r and theta if necessary. And whatever the expression is here also has to be converted. So pretty much everybody has to be turned into something to do with r and theta. Now in question similar to 7, they ask you to get the volume of something. And it's where this guy intersects with this guy. So far, so good. Now, do you recognize what this surface would look like in 3D space? What would x squared plus y squared plus z squared equals, in this case, 64? What would that look like in 3D space?
Sphere.
Sphere.
Great. What does x squared plus y squared equal 16 look like in 3D space?
Cylinder.
Say it again.
A cylinder.
Yes. Can you imagine I just draw it up here and then we come down, it'll probably come here like this, and then it pop out at the bottom. Now, can you imagine someone drilled a cylindrical hole vertically through a sphere, right at the top, and the piece of metal that you kept was the piece of metal that you drilled out? Can you, I don't know, like an apple corer. Can you imagine an apple, cylindrical apple corer, pump, right, and is a perfect, spherical object that you used it on, boom. And that shape would be very cylindrical, but wouldn't it have a curved top and a curved bottom? And we're looking for the shape or the volume of that shape. Now, how do you get the volume of shapes? Well, don't you do a triple integral of 1? And the E is going to be generated by this guy. So far, so good. Now we know that we're going to do a theta, an R, and a Z of 1 dz or dr d theta. So here is our puzzle. We got to figure out who these guys are. Which means I need a region on the floor to be the X and the Y. And then I have to figure out who the Z is. I'm going to use this guy here is the region on the floor, because basically isn't that what it would look like on the floor as you integrated upwards? And that guy is a 0 to 2 pi, 0 to 4 guy. Now I need to figure out, where do the z's go? Well, actually the z's end up being on the sphere. And this is the sphere. Now, if I rearrange this, are you happy with 64 take away r squared? And won't z be the square root of that? But in this case, isn't it above and below the xy plane? So they're going to be a positive square root of 64 take away r squared and a negative 64 take away r squared. Suppose they had added one more constriction or restraint. Suppose they said it was above the xy plane. That and that wouldn't change. How would this adapt?
The lower bound would be 0.
Right. Now, by symmetry, if I change this guy to 0, but I still wanted to know the entire volume, couldn't I just double that answer? Would you agree that that's slightly less work than the original version? Technically, it should be negative square root to plus square root, but there's a lot of symmetry going on here. So I'm saying 0 to there and doubling it would generate the same thing. It's a bit like the xy plane is right here, right? And the bit above is going to be the same size as the bit below. Well, what's that going to look like? Well, we're going to have 0 to 2 pi. We're going to have 0 to 4. And right now we're going to have 0 to some ridiculous guy that looks like that. I'm going to bring this r in, so it's dz, dr, d theta. When you bring the r in, this becomes rz. Plug that in for z. Can I skip some lines and say that's what you end up with? That r is there, and this becomes a z. Now, how are you going to tackle this fella? Well, it's variable separable, which means I only need to worry about how to find this guy. Since everything has an r, I can just use r, and this has got nothing. I guess I could give that the 2 if I felt like it. Right, I'm going to start dotting in a second. I need help. How do you integrate that ugly thing?
That's a pretty easy U sub.
Oh, I like the word pretty easy. I like the word pretty easy because it tends to mean I've done enough of these that isn't a big deal anymore, right? And would you agree that the U sub is 64, take away r squared, and it'll take you a while, but you'll eventually get an answer. And you're done. So when you get a question and it says, I want the volume of something, it's going to be 1 dV. When it says I want a volume of something, the r and thetas are typically going to be numbers, but aren't the z's going to be converted into a limit using r and theta? So if z happens to be x squared plus y squared, or whatever it happens to be, you'll convert that into r values, that or r and thetas in some cases, right? And use that as your start and finish z values. Any questions about that? Are we good? Okay, we're good. Won't do quite as much of this one. And this one is version of 8. they want the volume that's kind of the intersection of these two surfaces. So the volume is going to be the triple integral of 1 dv. And we're going to go theta, we're going to go r, and then we're going to go z. And 1 dz or d or d theta. I guess the first puzzle is what is that region, right? So if you imagine the first surface intersecting with the second, won't there be a boundary where they meet? And that boundary is like the shadow that you see on the floor. So imagine the first surface, this thing, which I believe is a cone, meeting up with this thing, which is what a sphere. You can imagine them, they intersect in a curve, and imagine you're looking at that curve from above downwards. That's what we're trying to find. So that means we got to figure a way of putting these together. In other words, where do they intersect? Now, if you convert this guy into z squared equals x squared plus y squared, then doesn't this become z squared plus z squared equals 18? And that gets me 2z squared equals 9, and that gets me z equals 3. And I went the wrong way. I mean, that is correct, but that's not very helpful, because I don't want to know it in terms of z, I want to know it in terms of r and theta. So here goes again. Z equals this fella. And x squared plus y squared plus z squared equals this guy. Only this time I'm going to do it in terms of r and theta. Would you agree that this is the same thing as saying z equals r? And isn't this r squared plus z squared equals 18? And this is z squared equals 18 take away r squared. And this is z technically plus or minus, but only one of them actually works. Why am I only going to use plus on this guy? Isn't that positive? So this is positive. So what does that tell me? It tells me that z goes from here to here. What do I know about, whoops, my theta guys? I've lost the darn thing. Okay, let's put the z in anyway while I'm thinking. My puzzle here is I'm not 100% sure which goes high and which goes low. I suppose it's that one. I guess I could check. Don't I just need to pick a number like 1? If I plug in r equals 1, that's 1. If I plug in 1 here, isn't that z equals the square root of 17? Would you agree that's bigger than that, and therefore that's the right order? I just did a test point. I guess I should have probably done it in GeoBra and looked at the thing, and then I could say, oh, that guy's high and that guy's low. Right. We now need to figure out, put that out this way, we now need to figure out the R value. And the theta value. So I guess I'll just write these guys down again. I have this fella, oh God time, and I have this guy. Which of these two guys really are going to tell us, I guess, what the x squared and the y squareds are going to be? Well, can't I replace that guy with him? In which case I get 2x squared plus 2y squared plus an x squared plus a y squared equals 18. That gets me 3x squared plus 3y squared equals 18. That gets me x squared plus y squared equals 6. Ah, gotcha. That's the circle that I was trying to find. The intersection of these two is basically substitution, right? You make one equal the other, right? And then you solve. Well, in this case, I'm just replacing that by this. And by solving, I get this relationship, which tells me it's a 0 to 2 pi, and it's what, a 0 to square root 6. Hope I didn't screw anything up there too much.
Why did you get 2x squared plus 2y squared?
Oh, I did screw up. Actually, it looks much nicer now, doesn't it?
Yeah.
But it could have been root 6, you know, in a different world, you know, a different case. So I had to find out what everything is in terms of the variables I needed to know. And I needed to know these two guys here in R and theta. So I had to find out where the two things intersected without the z's. And that gave me this. And once I see this, I say, ah, this surface meets that surface in a circle. How would that work? Can you imagine a sphere meeting a cone? Yeah, they probably would meet in a circle, wouldn't they? And the circle would be this circle here. At least the shadow that you would see on the floor would be a circle. Well, back to finishing this question off. Will you all say hi so you get attendance? This fella here is basically going to be theta equals 0 to theta equals 2 pi. This guy's going to be r equals 0 to r equals 3. This guy's going to have an r, then you tug in a z, so you are going to have to do one of these guys. That's the first one. And oh, and that guy. So you get an r times this fella and the r squared. Why do you get an r squared? Oh, why do you get? You're going to have an r here anyway, and then you plug in z equals r generates this guy. And this guy is a power rule. This guy is a u sub. ... It's a very quick finish to that question, and that's all I have time for.